March 12, 1927, Grand Central Terminal, New York City. The engineering reports from competing railroad executives visiting the New York Central's locomotive shops would never capture what they witnessed that winter morning. A passenger steam locomotive design with driving wheels that defied everything traditional railroading wisdom said was possible about high-speed passenger service. Through the steam and noise of the construction bay, the massive boiler of locomotive number 5200 rose from its frame using engineering methods that seemed foolish to industry observers. No conservative wheel arrangements, no acceptance of the proven 462 Pacific design that had dominated passenger service for 2 decades. No respect for the limits that kept locomotives safely anchored to the rails at speed. Yet this experimental Hudson-type locomotive promised performance that conventional Pacific designs could not match. In American railroading, master locomotive builders required proven wheel arrangements that balanced power and speed through time-tested formulas. Each experimental design was considered an expensive gamble that usually ended in failure. Different wheel sizes, different boiler pressures, different speed limits that no one could safely exceed. The New York Central was operating with locomotive philosophy the industry had never imagined practical. Massive 79-inch driving wheels, unprecedented boiler capacity, streamlined cylinder design, speed potential that would exceed not just competing railroads, but the very schedules that passenger service demanded. 300 miles from competing railroad headquarters, the most decisive locomotive revolution in American railroading history was revealing itself. Not in more powerful freight engines, not in traditional conservative designs, but in the systematic engineering that would redefine what passenger locomotives could achieve in ways traditional railroad thinking never imagined possible. The Pennsylvania Railroad's chief mechanical engineer stood in the New York Central shops that morning, examining the Hudson's enormous driving wheels with obvious skepticism. 79 inches, he muttered to his assistant, shaking his head. They've built a locomotive that will shake itself apart at anything over 60 miles per hour. Those wheels are too large, the reciprocating mass too great, the entire design too ambitious for sustained high-speed service. His assessment echoed opinions throughout the railroad industry. The Baltimore and Ohio's engineering department had calculated that driving wheels exceeding 75 inches created balance problems that no amount of counterweighting could solve. The Union Pacific's mechanical staff published internal memos warning against the New York Central's expensive experiment in passenger locomotive excess. The criticism focused on fundamental engineering concerns that seemed insurmountable. Larger driving wheels meant heavier reciprocating components, pistons, connecting rods, side rods, all moving back and forth hundreds of times per minute at high speed. The forces generated by this reciprocating mass could tear a locomotive apart, creating vibrations that would destroy bearings, crack frames, and make sustained high-speed operation impossible. Railroad trade journals published detailed analyses of the Hudson design, with most predicting failure. The Railway Age ran calculations showing that the Hudson's wheel arrangement would create dynamic augment forces exceeding safe limits above 65 miles per hour. The Locomotive Engineering Journal questioned whether any locomotive with 79-inch drivers could maintain schedule reliability on demanding passenger routes. But the New York Central had witnessed Pacific locomotives struggling to maintain the demanding schedules of premier trains like the 20th Century Limited, and they understood that passenger service excellence required accepting no compromises in the speed capability. The 20th Century Limited departed Grand Central Terminal at 6 p.m. sharp, carrying New York's business elite toward Chicago in luxury that rivaled the finest hotels. Behind gleaming passenger cars filled with wealthy travelers, a New York Central Pacific locomotive strained against a load that tested the limits of 1920s steam locomotive technology. John Morrison had fired Pacific locomotives on the Century Run for 8 years, shoveling coal into fireboxes that consumed tons of fuel between New York and Chicago. He understood the rhythms of these powerful engines, the way they accelerated smoothly from station stops, maintained steady speed through level territory, and labored through grades that demanded every pound of steam pressure the boiler could generate. But on the evening of November 3, 1926, Morrison noticed something that had become increasingly common on Century runs. The Pacific locomotive was struggling to maintain the tight schedule that New York Central's premier train demanded. The Century's timetable required sustained speeds of 70 miles per hour across level sections of track, with minimal time lost during station stops and grade climbing. The Pacific's up to 73-inch driving wheels could achieve these speeds, but only by running the engine at maximum capacity, pushing boiler pressure to its limits, and consuming coal at rates that left little margin for unexpected delays. Morrison watched the steam pressure gauge fluctuate as the locomotive worked through a series of moderate grades west of Albany. The needle hovered near maximum, indicating that the boiler was producing steam as fast as the firebox could generate it. At this pace, any additional demand, a stronger headwind, a slightly steeper grade, an unexpected slowdown requiring rapid acceleration, would make schedule maintenance impossible. The engineer, veteran railroader Thomas Chen, understood the problem without needing explanation. "She's giving us everything she's got," Chen said over the locomotive's roar. "But these Pacifics weren't designed for the schedules marketing keeps tightening. Every year they cut another 10 minutes from the timetable, and we're running these engines at their absolute limits just to keep up." The Pacific locomotive completed its run to Chicago only 15 minutes behind schedule, a delay that infuriated New York Central management and embarrassed a railroad that prided itself on punctuality. But for Morrison and Chen, the real concern wasn't this single delay. It was the recognition that Pacific locomotives had reached their performance ceiling. The problem wasn't power. Pacific locomotives could pull heavy passenger trains with adequate strength. The limitation was sustained high-speed capability. The 73-inch driving wheels that gave Pacifics their excellent acceleration required high piston speeds at 70 miles per hour, creating mechanical stresses that shortened locomotive life and increased maintenance requirements. Railroad executives had tolerated these limitations because no proven alternative existed. Larger driving wheels would reduce piston speeds and mechanical stress at high velocities, but conventional engineering wisdom insisted that wheels exceeding 75 inches created impossible balance and stability problems. That evening, in maintenance yards across the New York Central system, locomotive supervisors filed reports documenting Pacific performance struggles. The pattern was unmistakable. As passenger train schedules demanded higher sustained speeds, conventional locomotive designs were approaching their operational limits. The railroad needed a locomotive that could maintain 70-plus mile-per-hour speeds without mechanical strain, complete demanding schedules with reliability, and restore the performance margin that made premium passenger service possible. Whether such a locomotive could actually be built remained American railroading's most challenging unanswered question. The drawing board in the New York Central's locomotive design office stretched 12 feet across, covered with technical specifications that represented a complete departure from conservative railroad engineering. Paul Kiefer, the railroad's chief mechanical engineer, had spent 6 months calculating the precise specifications that would make high-speed passenger service practical rather than theoretical. The numbers told a story of engineering ambition that made traditional locomotive builders uncomfortable. Driving wheels of 79 inches, 6 inches larger than standard Pacific designs. A boiler producing 2 pounds of steam pressure, fed by a firebox large enough to generate sustained power at speeds conventional locomotives could never maintain. A total engine weight of 365,000 pounds, distributed across a 4 to 6 four-wheel arrangement that no American railroad had attempted for passenger service. The 4 to 6 four-wheel arrangement itself represented radical thinking. 4 leading wheels for guidance at high speed, 6 massive driving wheels for power, and 4 trailing wheels supporting an enormous firebox that could feed sustained high-speed operation. Railroad engineers had used the 4-6-4 arrangement for slow freight service, but never for passenger locomotives where speed and balance were critical. Kiefer's calculations showed that the Hudson design, named for the river along which the New York Central ran its premier trains, would solve the fundamental problems that limited Pacific performance. The 79-inch driving wheels would reduce piston speed by nearly 10% at 70 miles per hour, decreasing mechanical stress while maintaining locomotive power. The larger boiler would provide steam reserves that Pacifics could never achieve, allowing sustained high-speed operation without pushing the engine to maximum capacity. But solving these problems created new engineering challenges that critics considered insurmountable. The reciprocating mass of the Hudson's larger components, pistons, connecting rods, and side rods, would generate tremendous forces at high speed. Traditional counterweighting methods used for smaller locomotives would prove inadequate, potentially creating destructive vibrations that would tear the engine apart. Kiefer developed a revolutionary balancing system that distributed counterweights across all driving wheels in precise mathematical relationships. The counterweight placement followed calculations that accounted for every rotating and reciprocating component, balancing forces in multiple planes simultaneously. The mathematical complexity exceeded anything previously attempted in American locomotive design. Testing the balance calculations required building a locomotive, an expensive proposition that railroad executives approached with understandable caution. The New York Central had invested heavily in its Pacific fleet, and replacing those engines with an unproven design risked both enormous capital expenditure and potential operational disaster if the Hudson failed to perform. Kiefer made his case through systematic engineering analysis that left little room for doubt among those willing to study mathematics. The Hudson's larger driving wheels would reduce dynamic augment, the hammer blow effect of reciprocating masses, by distributing forces across more wheel rotations. The sophisticated counterweighting would eliminate the vibrations that critics feared. The increased boiler capacity would provide performance margins that made schedule reliability dramatically better than Pacific locomotives could achieve. On October 15, 1926, the New York Central authorized construction of the first Hudson locomotive. The decision represented either the most advanced thinking in American passenger locomotive design or an expensive mistake that would vindicate every critic who had questioned the railroad's ambition. The locomotive that would prove which assessment was correct began taking shape in the railroad shops, each component machined to tolerances that conventional locomotive construction had never required. Locomotive number 5200 emerged from the New York Central shops on February 14, 1927, its massive 79-inch driving wheels and streamlined boiler representing either revolutionary engineering or expensive folly. The test runs would begin immediately using track sections where failure would cause minimal disruption to regular passenger service. The initial tests focused on basic operation, whether the locomotive could move under its own power without the catastrophic vibrations and balance problems that critics had predicted. Chief Mechanical Engineer Paul Kiefer positioned himself in the cab alongside the test crew, instruments measuring every aspect of locomotive performance as 5200 took its first movements. The Hudson accelerated smoothly from a standing start, its huge driving wheels rotating with surprising grace for components that critics had declared too large for practical operation. At 20 miles per hour, the locomotive rode as smoothly as any Pacific. At 40 miles per hour, the expected vibrations from reciprocating masses failed to materialize, the sophisticated counterweighting system proving more effective than even Kiefer had hoped. But the real test came at speeds where Pacific locomotives began showing mechanical stress. As 5200 accelerated through 60 miles per hour, observers watched for the telltale signs of dynamic augment, the vertical hammer blow effect that could lift driving wheels clear of the rails, destroying track and locomotive simultaneously. The locomotive's motion remained remarkably smooth. Kiefer's instruments recorded dynamic augment forces well within safe limits, the 79-inch driving wheels actually producing less track damage than smaller-wheeled Pacifics running at the same speed. The mathematical predictions that had seemed too optimistic to skeptical railroad executives were proving accurate in practice. At 70 miles per hour, speed where Pacific locomotives operated at their mechanical limits, the Hudson seemed barely challenged. The boiler maintained steam pressure easily, the firebox consuming coal at sustainable rates, the entire locomotive operating with mechanical smoothness that suggested substantial performance reserves remained untapped. The test crew pushed 5200 to 75 miles per hour on a level stretch of track west of Albany. The locomotive responded without complaint, its riding quality actually improving at higher speeds as gyroscopic forces from the massive driving wheels enhanced stability. Railroad officials observing the test exchanged glances that mixed surprise with cautious excitement. This wasn't just meeting expectations. This was exceeding them in ways that suggested the Hudson design had capabilities no one had fully anticipated. News of the successful tests spread through the railroad industry with the speed of telegraph wires connecting competing companies. The Pennsylvania Railroad's mechanical department requested detailed reports, their previous skepticism replaced by professional interest in engineering that had achieved what they had declared impossible. The Baltimore and Ohio sent observers to witness subsequent test runs, documenting performance that challenged their own locomotive development programs. Even the Railway Age, which had published pessimistic analyses of the Hudson design, revised its assessments in light of actual performance data. But tests under controlled conditions represented only the first step. The real challenge would come when 5200 entered regular passenger service, hauling heavy trains on demanding schedules where mechanical problems would cause embarrassing delays and operational failures. Whether the Hudson could maintain its impressive test performance under the relentless demands of daily service would determine if Paul Kiefer had created a revolutionary locomotive or merely an impressive prototype that couldn't handle real railroad work. April 12, 1927. Locomotive 5200 stood at the head of the 20th Century Limited in Grand Central Terminal, ready for its first run on America's most prestigious passenger train. The assignment represented both supreme confidence in the Hudson design and enormous risk. If the locomotive failed on this highly visible route, the embarrassment would be both public and professional. Engineer Thomas Chen, who had voiced frustrations about Pacific limitations just months earlier, examined 5200 with the careful attention of a veteran railroader who had learned to trust his instincts about locomotive capability. The Hudson's size impressed him immediately. The massive boiler, the enormous driving wheels, the sense of power barely contained in the streamlined machinery, everything about the locomotive suggested capabilities far beyond conventional passenger engines. The departure from Grand Central proceeded normally, 5200 accelerating the heavy passenger train with the smooth authority that characterized well-designed locomotives. But as the train cleared the terminal complex and reached open track, Chen began discovering what the Hudson could actually do. At speeds where Pacific locomotives labored with wide-open throttles and maximum boiler pressure, the Hudson operated comfortably within its capacity. Chen found himself using only 3/4 throttle to maintain schedule speeds, the boiler pressure remaining steady, the locomotive consuming coal at rates that suggested it could maintain this pace indefinitely. Fireman John Morrison, who had struggled to keep Pacific boilers adequately supplied with steam, found his work dramatically easier. The Hudson's larger firebox and improved combustion efficiency meant less coal produced more usable steam. The grates cleaned more easily, the ashpan required less frequent dumping, and the entire firing process became more manageable despite the locomotive's larger size. The real revelation came on grades where Pacifics had required careful speed management to avoid stalling. The Hudson attacked these climbs with reserves of power that allowed Chen to maintain schedule speeds without the anxious throttle work and careful steam management that characterized Pacific operation. Where Pacific struggled and sometimes required helper locomotives, the Hudson simply powered through with mechanical confidence that transformed the engineer's experience. The first run to Chicago completed 14 minutes ahead of schedule, arriving with boiler pressure still adequate for continued operation and crew members reporting the smoothest high-speed operation they had experienced. Railroad management immediately ordered additional Hudsons, recognizing that 5200's performance represented not a lucky prototype, but a genuine breakthrough in passenger locomotive design. Competing railroads reacted with a mixture of professional respect and competitive alarm. The Pennsylvania Railroad accelerated its own passenger locomotive development program, attempting to match the Hudson's capabilities. The Union Pacific began planning high-speed locomotives using similar engineering principles. The Santa Fe studied the Hudson design for application to its premier passenger trains. But the New York Central had gained a substantial advantage that competing railroads would struggle to match. While others studied and planned, the Central was already building additional Hudsons and assigning them to the most demanding passenger routes. By year's end, 1927, Hudson locomotives were hauling premier trains across the system. their performance making the railroad's passenger service reputation as the Hudson's 779-inch driving wheels turned revolution after revolution at speeds that had once seemed impossible for sustained operation. The locomotive railroads had mocked the standard against which all passenger engines would be measured. December 7, 1929. The railroad industry gathered data that would permanently alter perceptions about steam locomotive capabilities. Hudson number 5324, hauling the 20th Century Limited through Indiana, had completed a 68-mile stretch at an average speed of 74.5 miles per hour, a sustained speed record that shattered previous American passenger train performance. The achievement wasn't a momentary burst of speed during favorable conditions. It represented sustained high-velocity operation across varied terrain, maintaining schedule speeds that conventional locomotives could only achieve briefly before mechanical limitations forced reduction. The Hudson had operated at these speeds for over an hour, consuming coal at sustainable rates, maintaining boiler pressure comfortably, and arriving at the next station with performance reserves still available. Railway mechanical departments studying the speed records discovered performance characteristics that explained the Hudson's superiority. The 79-inch driving wheels that critics had declared too large were actually optimal for sustained speeds above 70 miles per hour. At these velocities, the wheels' slower rotation reduced piston speeds and reciprocating forces that created mechanical wear in smaller-wheeled locomotives. The sophisticated counterweighting system that Kiefer had developed proved even more effective than original calculations suggested. Dynamic augment forces, the destructive hammer blow effect that limited other locomotives, remained minimal even at the Hudson's highest operating speeds. Track maintenance crews reported that Hudson's actually caused less rail and roadbed damage than Pacific locomotives operating at lower speeds. The boiler's exceptional steam generating capacity gave engineers operating flexibility that transformed schedule management. Where Pacific locomotives required careful throttle work and constant attention to steam pressure, Hudson's operated with reserves that allowed engineers to accelerate aggressively when needed, maintain high speeds effortlessly, and handle unexpected schedule challenges without strain. Passenger train crews developed strong preferences for Hudson locomotives, recognizing that these engines made their work easier and more reliable. Firemen appreciated the efficient firebox design that required less physical labor while producing more usable steam. Engineers valued the smooth operation and power reserves that eliminated the constant mechanical stress of pushing locomotives to their limits. Railroad executives discovered that Hudson reliability translated directly to improved passenger service. The 20th Century Limited's on-time performance improved dramatically after Hudson assignment, the locomotive's speed capabilities and operational margins allowing the train to maintain schedule even during adverse conditions that would delay Pacific-hauled trains. By 1930, the New York Central operated over 50 Hudson locomotives, with more under construction. The railroad's passenger service reputation had become inseparable from the locomotive that had transformed schedule reliability from constant challenge to routine expectation. Competing railroads struggled to match Hudson performance with their own locomotive designs. The Pennsylvania Railroad's K4 Pacific, long considered America's premier passenger locomotive, suddenly seemed outdated when compared to Hudson's speed capabilities. Other railroads began ordering their own versions of the 4-6 four-wheel arrangement, attempting to capture the performance advantages that had made the New York Central's passenger service the industry standard. The locomotive that executives had doubted, that critics had mocked, that conventional engineering wisdom had declared impractical, had become the fastest, most capable passenger engine in America. The Hudson's success represented not just vindication of Paul Kiefer's revolutionary design, but transformation of passenger railroading, from conservative operation constrained by locomotive limitations to speed-focused service enabled by engineering excellence. The final Hudson locomotives rolled off New York Central production lines in 1938, representing the culmination of continuous refinement that had transformed Kiefer's original design into the definitive American passenger locomotive. By then, 275 Hudsons operated across the Central system, hauling everything from local passenger trains to the railroad's most prestigious limited consists. The improvements made during 11 years of production revealed how thoroughly the railroad understood what made Hudson superior. Later versions featured roller bearings that reduced mechanical friction, improved valve gear that enhanced efficiency, and streamlined shrouding that reduced air resistance at high speeds. Each modification added to performance that had already exceeded original expectations. The Hudson's influence extended far beyond the New York Central's operations. Railroads across America adopted the 4-6-4 wheel arrangement, recognizing that Kiefer's once controversial design represented optimal configuration for high-speed passenger service. The Milwaukee Road, the Chicago and Northwestern, the Atchison, Topeka, and Santa Fe all built Hudson-type locomotives based on principles that the New York Central had proven through sustained operational success. But no other railroad's Hudsons quite matched the performance of the Central's fleet. The combination of Kiefer's sophisticated engineering, the railroad's demanding operating conditions, and continuous refinement through actual service had created locomotives that represented the absolute peak of American passenger steam locomotive development. Load tests conducted in 1940 demonstrated capabilities that still impressed engineers familiar with Hudson performance. A dynamometer car recorded Hudson number 5445, developing over 1,500 horsepower at 75 miles per hour. Power output that matched many diesel locomotives while maintaining the operational flexibility that made steam locomotives valuable for passenger service. The speed records established by Hudsons during the 1930s remained unmatched by steam locomotives throughout the rest of the steam era. The 20th Century Limited schedules, made possible by Hudson performance, became benchmarks that competing railroads struggled to match. The locomotive that critics had mocked as too ambitious had redefined what passenger train speeds were possible. World War II tested Hudson durability under conditions that would have destroyed lesser locomotives. Running extended hours, hauling overloaded passenger trains, operating with deferred maintenance that would have sidelined more fragile designs, Hudsons continued performing with reliability that validated every aspect of their construction quality. Railroad mechanical departments discovered that the sophisticated balancing and robust construction that enabled high-speed operation also created locomotives capable of withstanding sustained hard service. The diesel era that began after World War II gradually displaced steam locomotives from passenger service, but Hudsons remained in premier assignments longer than any other steam design. The 20th Century Limited continued using Hudson power until 1946, railroad management reluctant to replace locomotives that passengers and crews had come to identify with America's finest passenger train. The last Hudson operated in regular passenger service in 1955, concluding a 28-year career that had transformed American passenger railroading. Several Hudsons survived into preservation, museum pieces that represented not just locomotives, but the era when American railroads proved that innovation could triumph over skepticism, when engineering excellence could redefine industry standards, and when the locomotive everyone mocked became the fastest passenger engine in America.